Ron might
Yes.
be able to hear you.
Yes. So yeah, so I'm gonna go through this project we completed recently, QUASIM, so quantum computing for simulation in manufacturing. And yeah, I'm just gonna go through it hopefully at a high level so everyone understands. There are some technical slides. If you have any questions at any point, just ask me or speak to me after. So this was kind of the premise of the project. So in manufacturing, we use a lot of simulation in all different types of manufacturing. So we can shorten development time. So instead of having to build prototypes and then test them, we can simulate them on a computer, test them on a computer, and then we know what to build. So it keeps production costs down, more efficient. We get optimized products out of that before we actually have to build the product. Lots of pros. And on this column here, we see the quantum computing promises. And this is kind of what you hear in marketing all the time. I put promises in the inverted commas because maybe it's true, maybe it's not. Some of it's a bit hard to say. But this is often what you'll hear in, I guess, more business-centric things. So I wanted to put it here. So maybe by the end of the talk, we can also discuss about how true all of this is and when you shouldn't actually use quantum computing for your purposes. I doubt any of us are actually in industry here, but maybe one day. So yeah, we promise we get productivity gains. We can do complex optimizations, and the value will increase rapidly. And this last point is how they get the money. They tell you you should invest now so you can be ahead of the game. So when it comes, you own it. And one of the questions I get the most now is people asking me, should I invest in quantum computing? And that's a very hard question. That's not what I'm covering now. So the key questions for this project were, can we use quantum computing in simulations for industry purposes that make the task more efficient in principle? So maybe we can't implement it now, but if we had fault-tolerant quantum computers, would we be able to use those to actually help in manufacturing? And the second point is, do any of the NISQ algorithms we have now on NISQ devices actually offer an advantage or at least utility for manufacturing today? So we had two approaches here. So we had two different types of simulations. I'll show you in the next slide. But one, we had a numerical finite element methods approach, so very robust physics, but very computationally intensive. And the second approach so this was more for the NISQ algorithm, was to use near-term like parameterized circuits and with classical machine learning and see if we can help the simulation in that way. So the first use case we had is laser cutting. So we have these giant metal machines that cut out complex shapes of whatever you want really from these sheets of metal. So something like that up there. And this is almost fully automated, but 1% of the time something gets stuck and you have to hit it with a hammer and it will start working again. But the company wants it to be fully automated. So the task for the project was basically, if we give you a representation of what we want to cut out of the sheet, and we give you the path of the laser, can you model the heat of the object throughout the cutting process and see how it expands?
And that causes the problem.
Yeah, the thermal expansion causes it to get stuck. So if we can say it's going to get stuck before it gets stuck, then you know not to do it and maybe cut in a different way or do something differently. So yeah, that's the first use case. And then the second one was for cutting these blades on the jet engines. So they're cut and the water is just sprayed for like cooling and lubrication. But basically, these are really thin pieces of metal, and as you cut them, they vibrate. And if you hit the eigenfrequency, that's very bad because it can resonate and break. So the idea is we make a simulation of these blades, the different thicknesses and lengths, and we can work out the eigenfrequencies. And when you're doing the cutting, you can stay away from the eigenfrequencies and have a more stable system.
And what is a blisk?
A blisk is the name of these boards. So it's like on the front of an airplane, the thing that's spinning and pulling the air in.
Yeah.
Yeah. I also did not know. That's why they showed it to me. Yeah. So it's that's the industry side of the problem. So now we're gonna go through and say how we turn this into maths, and then
Into qubits.
and then that's the next part, how we made quantum solutions to these problems and how well they actually worked. Okay, here's a video of it. Sped up a little bit, but yeah, you can get an idea of how it spins and things. So for the simulation of the laser cutting, a lot of maths don't have to worry about the specifics, but it's all here if you want to ask me later. So yeah, the problem is if this thing expands too much, it will get stuck. And we can actually model this quite well mathematically already. So we can use finite element methods. So it's kind of almost modeling everything here like a spring and ball kind of thing. And we can do the thermal equations and we can calculate exactly how the heat will transfer if you give the density and the thermal expansion coefficients, etc. The problem is this is very computationally expensive and very slow. So even on their like big cluster computers that this company has, to do a small thing like this could take them 20 minutes to just work out like less than 2 minutes of cutting time. So, you know, sometimes it's better if they just let the machine get stuck. And so our part of the project was to say, can we make a quantum machine learning model that learns this expansion? So we feed it in some mesh and the path of the laser. And at every time step, we calculate the temperature of each node. And if it goes above a certain temperature, then we can say, okay, it's going to get stuck. And we had the idea in mind that this circuit should be small enough to run on a NIST device. So 5 to 10 qubits, somewhere in that range. And I'm sure the people that work with quantum circuits here know that that's not enough to do machine learning most of the time and get nice results. So, okay, and this is how they extract the real world data into a simulation. So we have these things being cut out. They have a whole lot of sensors and things, and they can take all of that information and convert it into a mesh graph. They use MATLAB for most of that, so also can be quite slow, and lots of proprietary software that the businesses pay for. So they want to avoid all of that when possible. So this is what our data set looks like. So on the right there, you can see what some object might look like. You can see it gets very complex in some parts where there's holes and things. Or this one's relatively simple. So this is one of the most basic data sets we had, where it's just got 3 time steps at the start, when it's cold, the middle, and the end. And then we also made, so we had some of their actual consumer data. So objects they're actually cutting out on their machines, and that had 1,000 to 200,000 nodes per object. And you can imagine you have to update that for 2 minutes worth of time steps or whatever. It's a lot of data. And we made some simplified data sets because we also weren't allowed to share those with the public when we publish anything. So it's just squares, triangles, and circles of various sizes, but the same data structure. So the real bottleneck here is how do I get that into a quantum circuit? And that was our first challenge at least. So here's kind of a visual approach of how we did it. So we pick one node on the graph, zoom in, and we pick one node as our central node, and we take the node and its neighbors. So in this case, we have 5, and we pass this into a quantum circuit. I'll get to that just now. So the first node is corresponding to the first qubit, and the neighboring nodes correspond to the following qubits in the circuit. And okay, I don't have enough time to explain quantum machine learning, but this is what a very typical quantum machine learning circuit looks like. So we have this layer here, which encodes our classical data into the circuit. So in our case, it's just encoding the temperature of that node and its neighbors into 1 qubit each. Over here is all our parameters, how the qubits entangle with each other. It works very similarly to how parameters work in classical machine learning. And then we measure just the first qubit, and that measurement will correspond to a temperature. And so what we're asking is, for this node and its neighbors at these temperatures, what will the temperature at the next time step be for this node? So this kind of works, but one problem you might be able to see immediately is, what if the number of neighbors change? Then do I have to train a whole new circuit for that? What if the ordering of the neighbors changes? Or does it matter? So we have to do things like that. So for the first problem, we did what we call remeshing. So basically pass through any object and make it uniform. So every node will now have the same number of neighbors, except the edge nodes, but you can account for that fairly easily. And then for the ordering of the neighbors, what we did is these parameters here that control the Z rotations are actually all the same parameter, because we noticed when we trained it at first, they were kind of convergent towards the same numbers anyway. And then this parameter is separate because it's for the central node, but all these X rotation parameters are also the same. So you can put the neighbors in any order, and it doesn't break your circuit. And then the next thing we did was try to figure out, we don't want to pass through the whole object every time and update every step, because if the laser is here on the other side, you're probably quite sure that the object's not heating up at that point. So we did a growing graph kind of approach. So basically we start with a node and its neighbors, and we say, okay, just in this time step, you only have to update these nodes. In the next time step, we pass the points where the laser has passed over, and then the neighbors of all of the previous nodes, so it kind of grows outward like that. And after a set number of time steps, we just stop updating that node, because we'd say, yeah, it's probably done with its thermal expansion at that point after X many seconds. So this was just basically a way to shrink the data set and decrease the processing time. And here you can see our results. So the quantum model is on the left here, and the classical model on the right. What the classical model was just a regression model with the same number of parameters. So our quantum model ended up with 12 parameters because we had more layers. Classical model had 12 parameters and same inputs asked for the same output. And unfortunately, as you can see, the loss of the classical one is about 3 times less than the quantum one. And also a lot more efficient. Yeah.
The like significantly less decrease in loss, is that due to the fact that classical computers are better developed, or is it due to the fact that the algorithm is better?
It kind of would probably point to the fact that the entanglement happening between the qubits in this model just didn't have any positive effects on the actual learning. So for this problem, you just didn't need a quantum computer to learn what you wanted to. But yeah, not completely hopeless though. So this was more a test of how do we process such large data sets on a NIS device, which we were able to do. And even if you were doing this with like a neural network approach, we tried that first. This did beat the neural network approach by quite a lot. It was just funny that the simplest thing we could imagine was actually just the best performer by far.
And this is simulated.
Yeah, simulated. I have some real results later, but for the other problems.
It's gonna be worse.
Yeah, so this is like also as good as you could get. There's no noise, there's no interference, etc. For a 5 qubits circuit. But if we look, so the top half was us trying to figure out the best structure of the circuit. You see these 3 here. So basically us trying to include the distance data between the nodes. So at first, here we're only including the temperature. But we figured if you're doing heat expansion, you probably want distance data between, because if they're closer together, they're more likely to transfer heat. So this was just this temperature data, and then this one was using these parameters here to encode the distance data. The second approach was just adding a qubit for the data, for the distance data in here, and just encoding it, so you doubled the number of qubits. And the third one was making a function like this that includes distance and temperature as one variable. And yeah, in the end, the making one new variable performed the best by far. This top block, we only did it for one time step. So that's why the values are so much better. We were only looking at one time step to another and taking the loss. But the good thing was, regardless of the way we did it compared to the classical way it's calculated, we had huge time improvements, even with the simulated hardware. So it's promising potentially in the future for replacing these FEM calculations. And at the bottom here, we were comparing how that growing graph approach compared to not using it, and then to a classical model. So the inclusion of the growing graph actually reduced the loss by a decent amount, but not enough compared to the classical. All this to say, when you take the physics of the problem into account, you can improve your models quite a lot by knowing the problem well and not just throwing the data at it, which it's not in the slides, but the traditional machine learning approach would have just been, I'm going to feed this mesh graph into a neural network and let it learn. And we outperform that by taking the physics of the problem into account. And then the second problem was the list milling. So just another slide to remind you of the problem. So we're drilling and cutting into these blades, and we don't want it to vibrate at the eigenfrequency. So there's a whole lot of maths that they use currently. This is how they currently calculate it. So they make mesh representations of each of these blades. So this would be like a ball and spring, also kind of simulation.
Is it finite elements?
Yes, finite element methods. And they run a whole lot of these simulations. And then they work out the eigenfrequencies. I'll show you how that looks on another slide. And the output is this graph here. So it tells you where the peak kind of resonance is at each eigenfrequency. And we want to aim for these low points. So yeah, this is the top one. You might be familiar with like harmonic motion. And yeah, we turn this into an eigenvalue problem. We have these matrix K and M, so stiffness matrix and the mass matrix. And this model can tell us these modes that you can see here, and the modes tell you what the eigenfrequency is. And so the idea here, so this work is one of my colleagues' work, so I can tell you details, but I might be missing one or two small things. So yeah, so we can turn it into this eigenvalue problem, get this response matrix. So we're turning a dynamic equation, which is the position as a function of time, into, and we use a Fourier transform, and now we have the force as a function of frequency. And then we can reduce it to an eigenvalue problem, get this response matrix and calculate that. But for hundreds of thousands of springs and balls, that matrix can be very large and very complex. So for this one, we had a fault tolerant approach. So basically, we take the stiffness and mass matrix, we make one new matrix out of them, and we encode this into a circuit. And the basic idea here is you can do a quantum Fourier transform. You set the circuit up right, which decodes the problem, and at the reading of the circuit, we get the eigenvalues, which would be correspond to the eigenfrequencies of that list problem. So the output of the circuit is going to give you the frequencies which you should stay away from in your manufacturing. Yeah. And so this is the real world results when we ran this on the IBM computers. So this is the system we were running it on, 4 balls and 3 springs. Because that's as much as we could encode into a real quantum circuit.
So in how many qubits?
This one was 6, I believe. Yeah.
So it's another method. It's not quantum Fourier transform. It's just another algorithm.
Yeah. Yeah. So this graph is directly from his paper, but basically these points here are the maximally mixed states. So the noise essentially, and these blue triangles here are the ideal solutions, which we can calculate numerically because it's a relatively small system. And so these points are the data, and as you can see there's quite a lot of different things. So the things on the right are error correction, and the opt is specific error mitigation optimizations that my colleague implemented. And so as you can see, as you go deeper in depth in the circuit, the solutions get closer and closer to maximal noise, which is expected but disappointing. And at shorter circuit depths, there is sometimes overlap with the ideal solution, and this one up here, but that's quite large error bars. So all this to say, it can work, but the hardware is not there for us yet to make it work. Yeah, so these are our main challenges for actually using quantum computing in industry. We've got the algorithms themselves, we don't exist yet or are not very optimized. So people like us have to make better ones. Not necessarily specifically just for industry, but we make generalized algorithms, we can apply them to things like this. Our quantum hardware is lacking at this point. It's improving at a decent rate, but we're still a while away from having it in industrial use cases at least. The scalability, so how large a system we can have. So even if we have a 100 qubit system, that's still maybe not enough compared to like a supercomputing cluster. And that's just going to also take time before we can use these algorithms on a large scale. Integrating it with current systems, so we can do all this, but then if I take this model to the company, like, okay, how do we run this? Like, how do we plug this into what we're already doing? And that's a big challenge, and there's companies that specialize in that, and it takes them 10 years before they can implement something into a company that's large scale like this. And then expertise and training, there's very few people that can actually do this at this point. And hopefully some of us will be the ones doing this training and things. And yeah, so the summary basically is we have some quantum algorithms which can provide value for the industrial processes, but we need quantum hardware to do it. And we also need to be very specific about what problems we're actually applying this to. The quantum computer is not just going to come in and make your business 10 times more profitable or something. You need a very good idea of the problem you're working with and a very good solution for your specific problem. And the kind of sad point is the NISC algorithms and hardware don't seem to offer any utility for real world problems, but they can change how we think about classical problems. So like the machine learning circuits I showed earlier, there have been a bunch that are now classically simulatable, and you can work out the same solutions classically, but there's still approaches that wouldn't have been come up with if we didn't have the quantum ideas. Thanks.
Yeah. That's well, it was really nice to hear the real world.
Yeah.
In a very protected environment, things usually work.
Yeah.
Are there questions for Rivan?
This is more related
Yeah.
to the hardware. What is the lack in hardware that is current or that we currently face, and also where is the where is quantum hardware being researched?
So the biggest problem with hardware is error correction. So there's a lot of noise when we're running any of these things. So this was done on the IBM ones, but excuse me, even with different architectures, there can be a lot of noise. Which just means when you run the circuit, it's not gonna give you the output you want. The second problem is the number of qubits in these computers is quite low right now. And because of that, you can't put that much data into the computer, which really limits what you can calculate with it. Like I'm sure most of us know Shor's algorithm. The the largest number you can do with it is very small with current hardware. The largest one I know is 21. There was a paper from China recently, but I haven't read it yet to know what the number in that one is, but I'd be surprised if it was more than 4 digits. And as for where they're being researched, that's all over the world. Not here, sadly, but that's kind of strategic, I guess. It's very expensive. So there's like where I work, they have a project where they're trying to build a quantum computer from like ground to finish just within Germany, Australia, Canada, the US, China. Everyone's trying different technologies, different ways of doing it, and there's no clear front runner yet either, which is good and bad. So it seems like certain types of quantum computers might be good for certain algorithms, simulations, others will be good for others, but it's kind of a waiting game to see what's actually gonna be used by people.
What quantum computer are they building in Jülich?
It's a superconducting based one. Yeah,
So like IBM essentially.
yeah, a transmon. Yeah. Yeah.
If you go back to that list of things that we need to do, that one.
Yeah.
You were a funding agency, you had to pick one. Which one would be the most important?
Those two. Probably the hardware first.
Which one?
Yeah. Because as much as we can come up with ideas, we can't test them. And if you think about machine learning now and stuff, a lot of it's kind of, we ran stuff and it worked. We didn't like fully plan out everything before we ran it. We just had some ideas and executed it and then tweaked it afterwards. And I think once more people have a lot of access to hardware, it will speed up a lot. Yeah.
Please.
So with the simulations you ran, the quantum simulations were a lot faster. But they were also worse. So is it actually significant that we can get worse answers quicker?
It depends on the tolerances of your specific problem. So in this case, neither the classical nor the quantum machine learning was accurate enough. But I think with the classical one, you could tweak it more and have speed gains that are significant with the like accuracy not being bad enough. Because when we're at these temperatures, the temperature range is like, say, 0 to 5,000 degrees. If you're off by 10 degrees, it's probably fine because you're just trying to make sure it doesn't go past a threshold. So it's really problem specific for what you want to do. Yeah.
Yeah, thank you for your talk. I think you mentioned it, but I probably missed it. When you're showing like the network for the thermal expansion, did you pick that out to know because that's where the blades start cutting?
Yeah, so yeah, that's where the first nodes that the laser touches are like the first ones we take in, and then we consider its neighbors, etc., and go out from there.
And then also, like in the second slide, you talked about why I'm pretty sure you said like why quantum computers won't take over classical computers completely. Why do you think that is? If they like get a speed up?
Because they don't have a speed up in every single thing.
Okay.
So there's some things that they're at best just as good at, and we already have all these classical computers. So we're not going to just throw them away. You know, we can use them in parallel. You can think of it like having a graphics card in your computer. You don't use it for everything. You use it for the things it's really good at. So
It's just expensive to use the program.
yeah, and yeah, so like it can always do, in theory, everything a classical computer can do, but that's also a lot of stuff we'd have to work out again instead of just saying we have it. Yeah.
You normalize the temperature, right?
Yes,
To
yeah.
the range, you do all circuit, you measure the output using some probability, right? Do you then just unnormalize that to? have
Yeah,
it?
exactly. Yeah, so at the start of the part of the pre-processing is figuring out what the maximum temperature inside the simulation is, and then normalizing with that.
I think this question's on my.
Yeah.
Sorry.
So
I have to do it self-service.
yeah, sure. So where can I apply for the Q nickel or Q silver diploma to gain certifications?
Okay, that's a question not for you.
Yeah.
Then but we can share it later. Just drop us an email.
Yeah, just drop.
Are you?
I'm not online, but maybe.
Then type it in the chat.
Yeah.
To email you or me or something.
Looked at the confirmation of element 117 transfer email. Can exotic states of matter be built better on quantum computers? Hopefully. So the idea is basically, if we think matter is quantum, which we're fairly sure about, or that quantum mechanics is valid at least, and we want to do simulations of very small scale things like tens of particles or something, shouldn't we use a quantum computer to do quantum simulations as opposed to a classical one? And that's a very active field of research, also called quantum simulation, so don't get this confused with that. That's probably the more standard way of using quantum simulations. Yeah, so the idea is we can test out different structures and interactions between quantum particles and encode them onto quantum processes and see what the results are in a very similar situation where instead of having to do the experiment physically, we can simulate it and only do the ones we think will work. What's the role of superconductors in the race for better hardware? And are there alternative methods? Yeah, so the reason superconducting qubits are the most popular is because we know how to build superconducting silicon chips very well. Whether they're the best is a different question. I don't think they are. They work in some things, and now there's a lot of error correction on them, but yeah, there's a lot of different technologies like photonic quantum computers, which use lasers and ionic based, so with atoms and like Rydberg atoms as the CPU, basically. Yeah, and I'm not an expert on the hardware or anything, but there's a lot of promise out there, and every technology has its pros and cons. For some are way slower gate speeds, so they're slower processes, but they have less noise. The superconducting ones are a lot faster, but are much more prone to noise. Has there been applications and developments for quantum internet? That's probably a better question, Francesco.
That's another thought.
Yeah. Yes, the satellites.
Yeah.
And okay, yeah, the last one is just a request for contact if you're an expert in that field. Yeah.
I have a question.
Yeah.
In Jülich, you're actually trying to explore industrial uses of quantum computing.
Yeah.
Give us 2 examples. Are they looking also in other industry branches?
Yeah, we have a
chemistry,
new
medicine?
project
Yeah.
currently that
Yeah.
I'm working on, which is with Mercedes. The one use case is quite similar to one of these, also with finite element methods, and the others with like a logistics company. So
Okay.
using the quantum computer. So one thing I didn't touch on is like quantum annealing quantum computers,
Yeah.
and basically they're very good at optimization problems if you can map your optimization problem to the quantum computer. So that's one thing we're looking at, and yeah, hopefully we have more quantum chemistry based stuff.
Okay, that's probably to hear.
Yeah.
It's- But you don't do chemistry.
Not me personally. We have some people we're affiliated with that do chemistry.
Because even there it's difficult to show.
Yeah.
The logistics one also is with Mercedes or
No, with a different company.
Germany has a lot of them.
That's
Yeah.
espionage.
Okay, can I ask a quick question? Can you go back a few slides? Back, here. Okay, here, you mentioned something about entanglement that
Yeah.
didn't have any
So
advantage, something like that.
if I show you this circuit, the learning is learning these parameters which just rotate the single qubit, or learning these parameters which entangle the neighboring qubits to the central qubit.
Okay.
The idea with the classical model was I feed it exactly the same thing, but without this layer. So it only has these parameters. So it's
Just
only
rotation.
just rotating or adjusting just the temperature of one temperature. And yeah, so it would basically said the entangling isn't adding.
Oh, you got the same result.
Well, we have better results.
Better result.
Yeah, 3 times better.
Yeah.
Yeah,
Is it a little bit like, without the RZ?
yeah.
Euler method. And with RZ, it becomes Runge-Kutta.
Exactly, kind of, yeah.
Yeah, okay, that's very interesting.
Yeah. So,
Okay, that's very interesting. To explore.
But essentially, we expect that entanglement should make your model like.
it should, but the thing is that's why I say it's very problem specific. So
Yeah.
for this problem, We didn't, and I mean, we know exactly where these numbers came from. We calculate them with the finite element method, so it's just saying there's nothing hidden in the quantumness of it that we can't see or something.
Because I remember Maria Schott also mentioned something about this. They
Yeah,
had entanglement and they didn't see any
yeah,
significant
That's the-
change.
exactly. That's a good sanity check once you've trained your circuit to remove the entanglement gates and see if the output changes.
Okay.
And it doesn't.
It depends.
That's-
We didn't do that direct
Yeah.
experiment. So.
So, there's a question there, please.
Hi, nothing about quantum computing, but just curious about the physics models you use. That you mentioned the similar high emission space like from vibrations, lens vibrations. Is that do you use any other models as well?
No, so that stuff came directly from the industry people, so that's what they're currently using in their models. There's almost definitely ways to improve those models without doing all of this. But yeah, we can
Just out of curiosity, what packages do they use to do the finite element?
MATLAB.
MATLAB.
Yes, that's also why it takes so long.
Oh, okay, no,
Uh,
that's a much better solution.
Yeah, but it's when your company is so large, it's very hard to change something. So they'd rather just keep using what they're doing.
That's interesting.
Yeah,
It's not a startup mentality.
it's the opposite.
More questions for Rivan? No? Okay, then Rivan, thank you so much. It was really nice to have you and good to know that in industry they're not much cleverer than here. So let's have the same problem. So, very
No,
good.
thank you.
Excellent. Thank you very much and good luck for the last sprint. Huh? Thank you. Thank you very much. And at sorry, before we clap, at the public lecture at 4, do you know where to go? The three of you.
I know the name of the place, but.
Okay, it just you know,
know,
when you get out of the physics building, you go 3 steps down, cross the road, another 3 steps down, 1 floor up, and there is the SAQuTI. So, and there are nice coffee shop just opposite. If you need.
Drive by group.
Drive by group. Yeah, you might meet us there just now. Since there are so many, why don't you take a seat and I take a photo? They will take lots of photos. I'm very good.
You should be in the photo as well.
Yeah, no. I was from movies. Wonderful, big smile. Thank you very much. Zack. Excellent. Thank you. That's for history books.
Pioneer.
Yeah. Excellent. Thank you. Yeah. Thank you very much. Thank you.